So I would like to tell you about online facility location. So I guess you all know facility location. I will tell you about some online variant. I will discuss there like multiple options for making it online. This will be a joint work with my colleagues from Wrocław, Marcin Wisławski, Marcin Bon, and Marcin Polski. Okay, so okay, I can use it. Okay, so in facility location, you have like a process, like facilities and clients, and need to provide service to clients by connecting them to facilities, and to this end, you open some facilities. You pay for opening and pay for connecting. And in the online version, there's also some notion of time. So we will always have space and time. I will draw space horizontally, time vertically. And this other online facility location model, where the picture for this model, the idea is that clients arrive over time, and your algorithm can open facilities, but then these facilities, they stay open forever. And once you decide to open a facility, then later clients can connect to it. So that would be the standard online model. This model was studied, and it is known that log and overlog and competitive algorithms are possible. Better competitive algorithms are not possible. So I will no longer study this model. let's move to something that's interesting. Open. Okay, so we will study facility location with delay. We could think with waiting, and now again, clients come over time. They show up, and we are about to open facilities. But now these facilities don't stay forever. They are just for a while, for a moment. But these clients don't have to connect immediately. I mean, if they had to connect immediately, it would be just independent instances of facility location. But now we allow these clients to wait and later connect, so they would pay for waiting and then pay for the distance, and so they connect. So that's a very natural model. So what is known that for this model, log-n competitive algorithms are possible, and it's very recent. Only last year, they got log-n competitive algorithm. In 19, there was log-square competitive. So these problems are only very recently studied, and it remains open if you can do constant competitive. Okay, let me say what. So competitive analysis is almost like approximation analysis, but you compare yourself with a cost of a solution computed by an algorithm that has all the information. Okay. So it is open if you can do it with constant factors. But before I go further into facility location, let me tell you about related work.
Excuse me, Jarek, can you explain me the last sentence here? What do you mean, even in the offline setting?
Good. So you can consider the same problem, but knowing all data in advance, like knowing when clients will arrive.
Yeah.
There are different waiting cost models. So in perhaps the simplest model, and the one that we will be studying, is that you pay waiting cost linear of the time.
Yes.
In this setting, the offline constant factor is known. But in the other versions, where, for example, clients come with a deadline, it's open even in the offline setting. So this is not much studied, and there are nice open questions also in the offline setting. So there's related work. You can view it. Okay, so it's related in the sense that you also study problems over time, but now it's no longer facility location. So you can view that this is some kind of service over time, that clients can wait for service and then you service them. There's quite a number of settings that fit into a framework that can be described in the following way. That the service you offer by connecting clients to some predefined node, you can think like a root node. And to service a set of clients, you need to buy like a Steiner tree that connects these clients to this pre-selected root node. And now, depending on how complicated is the metric, in this framework fit very different problems. This top line, it fits when the metric is single edge, so clients arrive, say, at the bottom and the root is at the top. So these problems were studied by two communities, operations research people call it lot sizing, systems people call it TCP acknowledgement, and studied for online setting. I'm not able to give credit to all the work that was done for this. I'm more interested in the lower part of the table. See, you see this metric can get more complicated. Somewhere here we get joint replenishment problem. Here we talk about aggregating on a tree with constant number of levels. And you see here is we have, if the input metric is a tree, the offline problems, they have constant factor approximation algorithms. There are some primal dual algorithms possible here. But for the online setting, only for constant number of levels, we have constant competitive algorithms. But for a tree, already for a tree of where the number of levels is an input, we don't have constant, we have competitive ratio, it's a function of the depth. And for general metric, this paper that I mentioned to you, also in the Steiner tree over time, they get logarithmic competitive algorithms. Interestingly, recently, Neil with his student, they got a result that the Steiner tree over time problem studied offline, you can beat the logarithm ratio, you can get a log approximation algorithm, it remains open if you can do a constant. So there's some recent work. Okay, but let's go back to the facility location. So we will be studying facility location all the time. So to service a set of clients, I need to open facilities and connect them to these facilities. So that's, we are back to the previous slide. That is, we have these clients, they arrive at the time and we pay for the waiting time plus connection time. And as I told you, here we have logarithmic competitive algorithms. And now I will depart from this model to make it slightly easier because I want to do something with constant factor. So I will show you that we can do constant factor competitive algorithm, but for slightly modified models. And here comes the modification. So I would like to allow, you could call it late connections. So the time goes up. I decide to open this facility for the two clients. And later, another client wants to connect to a facility previously open. So in this new model, there's waiting possible on both sides. So you pay for the waiting until the decision, but you also pay for that you kind of come too late for the service. So you could think maybe the products are not fresh or something, that you come too late.
Yeah, I mean, you wouldn't do both green and red.
You would actually do for an online algorithm. So offline, you would never do it. If you see the whole instance, you would always have just one type of waiting, but actually this is essential for online algorithms to first wait a little bit and to see if maybe other alternatives will show up.
So should we think about the facility as being open for some time until the clients?
This is where you can think of it. So they appeared in time space, and you could consider reusing it by looking back in time. There was this facility.
But the late fee is from client, not from facility.
It's per client, yes, this is important, it's per client. So, well, actually, what I'm showing you is what I can solve with these primal dual methods that we will exercise.
That's online again. Right?
This will be online, so clients arrive all the time, and I online make decision when, if I want to open a facility, and then I online make a decision to connect. So this decision can be later than the decision to open facilities. Okay.
So in the offline setting, it's just a facility location with time being like another dimension in your space. And the metric being asymmetric.
The metric being asymmetric, it brings some difficulty, but I can still tweak the Jane-Vazirani algorithm to get 3 approximation for the offline version with linear delays already in this model without going back.
Oh.
So offline, linear delays, I can do 3 approximation. But online, this is, yeah, we cannot do this online, it is open if you can do online. But online we can do with this other direction. Good. Okay, so the result is that for the two-sided variant, we get a bit less than 4 competitive algorithm. And for one-sided weighting, we get tiny improvement. Now it's log n over log n by a reduction to two-sided weighting. So the main result will be this one, but we also have a reduction from two-sided to one-sided, online reduction.
Right. The cost when you're late, does that have to be the same as the waiting cost? Or otherwise, why couldn't you just
For this algorithm to work, it has to be, there has to be a relation, like constant factor relationship. It cannot be like arbitrary. Okay. So here's small font, so maybe you don't want to read it all. Those of you who know JMS algorithm, so J9 and Sabelli. So the idea is that these clients, they will grow some kind of dual budgets. And here I call it connectivity budget of a client, but actually this client arrives and then time flows, and then this client will experience having more and more budget, and this budget can be used for connectivity, but it can also be used for paying for opening a facility. And here is this is a way you calculate how much a client can contribute towards opening a facility in a particular place. So there's just budget minus distance, and you take a maximum of 0, so you don't have negative contributions. And the idea is that at any point in time, if the contributions of the active clients are enough to pay for opening, you just open. But then clients become inactive once they are open, so they kind of withdraw their contribution. So that's not a standard primal dual like Jane-Vazirani that produces dual feasible budgets. This will be slightly infeasible, but you do dual fitting analysis to scale it down to produce dual feasible solution. Right. So let me show you a picture how this budget looks like. So this space could be more complicated, but for simplicity sake, it's like a line. But then there's a time, and this will be like L1 ball in 2 dimensions. So you can think of this budget after waiting that much. At this point, the client has budget that would suffice to travel within this region. So you can think later, at some point, the total contribution from 2 clients is enough maybe to open a facility in this place. So they would open facility and get connected. And once they get connected, their budget kind of disappears from the picture. But then comes the 3rd client that wants to get connected. She starts to grow her budget. At certain point, she has this budget that would be sufficient for connection, but this is not sufficient to pay connection plus delay. So she has to go further, but she waits a bit longer, and then her budget starts to be sufficient for connection plus delay, and then she connects backwards. And here it's very important that this connectivity budget grows slightly quicker than this cost for delay, because I need that this ball also grows in the opposite direction so that she can finally reach this previously open facility. Okay, so this type of algorithm we can construct, and how do you analyze it? So what you do, you write a, okay, so that's again the algorithm, how you analyze it, you write a factor revealing linear program. What is this? It is a model of a fragment of an instance and of the behavior of the algorithm on a fragment of the instance. So you look like at an optimal solution, and you can think of an optimal solution as a collection of stars, how clients are connected to a single facility, it's a star. And you model how bad it can be for a single star fault. So what could be the dual balance? So here in the top, you see it's like a cost of the algorithm. So this will be like service time minus arrival time. So that's how long did this client grow the budget. And that's how much cost he will pay. So one will be paid for waiting, and that much will be paid for. So that's how much of this connectivity budget the client gets. The denominator is the cost of the star of the optimal solution, and you get some constraints related to the execution of the algorithm. And interesting thing, if you know the JMS analysis, there is a relatively simple constraint that we refer to as triangle inequality. And now we get something pretty complicated in place of the original triangle inequality, because now we travel both in space and time, and it's a little tricky to encode it. I have a picture explaining for the meaning of this. So you imagine client I, who arrives here, is waiting until here, and the constraint says that this client must consider connecting to an already open facility that was open for client J, who got connected earlier. So it must be no more than this distance. The first part is just distance between clients. This you can measure in terms of service times of the two clients. And this last part can be measured by the connectivity budget of this client when he got connected. So you just put these three pieces together, and the connectivity budget of client I should not be more than these three pieces together. And in the end, you get such a fancy constraint, which you can put into the program, and you get this fancy program. So I claim this program is a valid bound on how big could be the cost of the algorithm versus opt on a single star of size k. K meaning k clients connected to a single facility in opt. So what you can do? Well, you can of course compute it for different values. So gamma here is a parameter that I set in this algorithm design. K is for the analysis, so I can plot it for different values, gamma and k. And I get some numbers. So for a while, ignore the blue part. I get the red curves. So the horizontal axis is I'm choosing different values of gamma because I want to find the best gamma for my problem. The different curves I get here are for models of different size. So I test k equal 100, 500, up to 1500, and I get these red curves. But there is a problem in this type of analysis. It's common to all JMS-like algorithms. So what we get is a bound on fixed size of opt, but you actually want infinimum over k of these bounds. And there are different approaches to that. There was the original argument by J. Martin Severi. It involved constructing like a sequence of duals and then well, analytically proving that these duals converge to some value. And well, maybe you like these arguments, but I never could digest this kind of argument. I never could get intuition why such sequence works. So I really wanted to do it differently. So here I want to show you an example of a different type of analysis. And so I will modify the linear program. And instead of this crossed out constraint, I put a different constraint. Who can spot the difference?
The index is different, plus one.
Yeah, that's the only difference. Summation has one more term. And we can formally prove that a value of the modified LP for any k is an upper bound on the whole sequence of lower bound LPs. This is not too difficult. I will not go into details, but it's like less than one page argument. You take solution from one, you produce solution of the other. Okay, so I get another program, I compute it and I get the blue values. And the blue values are now legal upper bounds. And so I can read that the blue dot is an upper bound on the approximation ratio, and the red guys I can use as a lower bound on my analysis, so I actually see how well I approximate this actual value. Okay, so I want to advertise it to you as an alternative way of analyzing these sequences, and in particular, I first made this factor revealing LP much more complicated by having this fancy constraint. So you could expect that manually constructing dual would also be more complicated, probably. But with this trick, I had a clean proof of that. I use a different LP, and now you have to trust an LP solver to get to a number. So maybe not everyone likes it.
You have to trust an LP solver to do what?
I mean, to calculate a number. Okay, so some people complain that this analysis is complicated because you need to solve like a linear program with 1500 variables.
I see, but you can use a constant value to upper bound an
Yes.
family of things.
So in particular, if you take k equal 100, you just get less accuracy, but it's a fixed size object.
It's correct, right? No,
Yeah.
it's fine. Don't worry.
I like these trade-offs because they show kind of the more computational power you put, the better bound you get. I mean, of course, not always that works, but here's an example. Okay. Okay. So that's it for the. Okay, I can always tell you more details, but that's all I wanted to tell you about this primal dual program for the two-sided weighting. Well, now I can shortly tell you how to reduce one model to the other online. So what's wrong with this? When this solution to the two-sided weighting becomes illegal for one-sided, it is the case when you want this late connectivity, because my algorithm, when it was opening a facility, it was connecting some contributing clients in an online way. So there was nothing wrong with in the original model. The only problem was these clients who kind of illegally wanted to connect it to something previously open. Okay, question to the audience. So what should you do in a reduction for this late client? Again, I guess. What do you do?
Open it again.
Open it again, yes. So solution is open a second copy. Well, maybe there are more of these clients, so maybe you want to open it a bit later to collect more of these clients. And now what you need to take care of is that weighting up is no more than what we paid for weighting down. I mean, not more than some factor away of that. And that's essentially the main idea, but but you need to argue that you open just a bounded number of copies, and you need to argue that this weighting up is at most some factor away from the weighting down in the original thing. And this is an online reduction, so you can imagine you run somehow in background you run your algorithm with two-sided weighting, but whenever my algorithm for two-sided weighting says connect to already open facility, I say, well, maybe I don't connect yet, but I will later have another copy and then I will connect. So here's a sketch of the argument how you do it. So the first copy you open when in the moment when total weighting up of these clients that come between the first and second copy, the total weighting up equals the total weighting down of these clients in the simulated two-sided variable. There will be such a moment. So this total weighting up will be continuously growing, and this total weighting down will be kind of also growing in steps, but there will be a moment that when these two quantities equal, and that's a good enough moment to open the second copy. And then what you do, you will open more copies, but somehow these distances will form a geometric sequence. So you will use some delta that's of this order, and you will say that each new interval between facilities is delta times longer than the previous one. And then you can argue that the number of clients that connect late to this facility will decrease between consecutive copies. It will also decrease geometrically. So that number of extra copies will be enough. There will be no extra client left afterwards. And for every single client that comes in between here, you can argue that originally it wanted to weight down, but now it will weight up. But this weighting up will be at most data times longer. And so this is not like deep mathematics. That's just a reduction that in online algorithms they did like such reductions. Okay, so I will slowly conclude. And okay, so we demonstrate how to analyze JMS somewhat differently. At least one fragment of the analysis we do in a way that I like better, it's simpler. We got this one competitive algorithm for two-sided weighting version. You may find it somewhat artificial, this two-sided model, but that's like a first example of this type of problem that you get a constant. I mean, all previous online algorithms in general metrics with delay, they had logarithmic competitive ratio, so it is some step forward. Okay, what remains open? It remains open if you can do constant competitive for one-sided model. We did not disprove that. It's unknown. And it remains open in the offline setting if you consider other delay costs, not just linear weighting costs, but for example, there's a model with delay, so a client, rather than having weighting cost, he or she has a constraint not to wait longer than until some deadline. So there is a model with deadlines, and for example, we don't know if online facility with deadlines can be done with can be solved in constant with a constant approximation ratio. Well, I would really like to answer this question.
So just to understand, you need to distinguish. I mean, this has to be different from non-metric facility location, right?
So here I'm assuming there is metric. Yes.
I mean, there is some. No, I mean, the general weighting costs are not general enough to capture. I mean, maybe they are monotone. They have some properties that.
Okay, okay. So for many of these problems, these like service over time problems, these general costs. When I say general, there's like small we just want that they are monotone, non-decreasing, and you want that they are left continuous. And these two conditions were sufficient to translate algorithms with linear delay into algorithms for this more complicated delay. But somehow for facility location, we don't know how to do it, even in the offline setting. So that's, I find it interesting. So it's an example that somehow facility location is maybe different from those other problems. Yeah.